Hi, and thank you for joining today's briefing on NASA's journey to Mars. I'm NASA Public Affairs Officer Trent Parado. NASA's preparing for a very important milestone 2 days from now with the first flight test of the Orion spacecraft. Now, Orion's designed to carry astronauts farther than ever before, enabling future human missions deeper into space, including to an asteroid and to Mars. And Thursday's flight test will be an important next step in the development of that spacecraft. But it's also a critical next step for what we call NASA's journey to Mars. And we're here for an hour to talk a little bit more about the flight test in context and what the journey to Mars means. We have a new graphic that you'll be able to see today many times throughout this program, as well as on nasa.gov. In fact, it's the image of the day today on the homepage. And you can also find it on social media and share it using the hashtag Journey to Mars. And we'd invite you to join the conversation there and help engage with us as we discuss the journey to Mars here. So we have a distinguished panel of experts here with us today to help better explain what the journey to Mars is, how NASA's science, human exploration, and technology are all working together to accomplish NASA's goals on Mars, but also help enable those future human missions to the Red Planet. Let me begin by introducing the guests we have here with us at NASA headquarters in Washington. To my left is Jason Cruzan. He is the director of the Advanced Exploration Systems Division of the Human Exploration and Operations Mission Directorate at NASA headquarters in Washington. Next to Jason, we have James Reuter. He is the Deputy Associate Administrator for Programs of the Space Technology Mission Directorate. And we have Jim Green. Jim is the Director of the Planetary Division of the Science Mission Directorate here at NASA headquarters in Washington. Now let me turn it over to my colleague Mike Curie. He's at the Kennedy Space Center in Florida, where we have some additional guests joining us to speak from there. Mike?
Thank you, Trent. I'm pleased to introduce our panelists here in Florida. To my left is Mike Bolger, the Program Manager for the Ground Systems Development and Operations Program at Kennedy Space Center. And to his left, Chris Crumbly, Manager of the Space Launch System Spacecraft Payload Integration and Evolution at Marshall Space Flight Center in Huntsville, Alabama. Trent?
Thanks very much, Mike. Okay, so we'll begin here at NASA headquarters with remarks first from Jason Cruzan.
So I'm going to start a little bit about explaining how we get from through this entire journey to Mars. Obviously, today we're starting with a very active human spaceflight program in low Earth orbit with the International Space Station. But going from where we're at today with the space station to distances like Mars is extremely challenging. We describe this kind of period of going from what we call Earth-reliant to an Earth-independent phase, meaning building the various systems and capabilities we need to advance human spaceflight to these far-off destinations. So we build upon that heritage with our International Space Station, and today we're testing advanced technologies and environmental life support systems, the habitation systems that we have, various autonomy and time delay experiments, along with our very active human research program on the ISS. These are teaching us some of the fundamentals we need to learn about living in space for long durations. With this week's flight with Orion, we're now entering into the next phase of advancing our capabilities into what we call our proving ground activities. In this proving ground, we are going to move further from Earth into the cislunar space and orbit around the lunar distances and look at how do we advance the habitation that we need for deep space transits to Mars? How do we look at the propulsion systems and large-scale moving of objects and living in that environment that we have in deep space? And preparing things like how to do EVAs in deep space and the overall mission objectives that we would want to advance on the way to Mars. All of these will be building upon the fundamental capabilities that we need to take us to the distance of Mars and get us ready for not only the transit, but also the surface activities that would come with a Mars mission. I want to talk about specifically also about our asteroid redirect mission as well. This is another activity that will be coming in the future and how that may fold into our activities and capabilities that we need for Mars. With that, we're going to be advancing things like moving large objects in space, looking at how to do those EVAs in deep space, and then moving into next generation advanced propulsion systems like solar electric propulsion that James will talk about here in a second. But But it's really critical as we move from this Earth-reliant phase to Earth-independent phase that we spend some time advancing those capabilities, get the confidence in those systems, and figure out how to operate in these extreme environments safely and reliably on the long transit to Mars. It's interesting to think about these distances that we have that we're coming on these kind of journeys. From the space station, we're mere hours from returning a crew safely to a hospital if we had an anomaly and such in space. On distances like on our way to Mars, if we have anomalies, our actual scenarios for recovery are actually aborting to the surface of Mars, or at least a minimum, you're still on a long-duration mission for over a year trip home. So this requires us to advance those capabilities in a very stepwise and systematic way to allow us the confidence to send humans on these long trips. We're working very closely with our other mission directorates, and you'll hear that here from my colleagues in science and the technologies that we need from the technology folks as well. And with that, I'll turn it over to them.
Okay, James.
Okay, as Jason alluded to, there's many technologies that are necessary if we're actually going to send humans to Mars. These technologies support those capabilities that Jason referred to. One of those is how do we get there and get back? If we tried to take everything that we need to live or to get down to the surface of Mars and get back up and get home, to do that with conventional rockets would require the vast amount of mass that you would take up into space to be the propellant to just get to and from Mars. And so in order to reduce that and make trips to Mars more affordable, one of the key technologies that we're working on is solar electric propulsion. Now, solar electric propulsion has been around for a while. We're actually using it on the Dawn mission. It's used on many commercial satellites today to do station keeping. But the kind of solar electric propulsion, the high-powered solar electric propulsion that's necessary in order to take cargo and logistics and accommodations to Mars requires a significant step up in the capability of solar electric propulsion relative to where we are today. And that's one of the key technologies that the Space Technology Mission Directorate is working on in conjunction with HEO. And the advantage of working on this high-powered solar electric propulsion is that it's also a benefit to the commercial space industry, and it is a direct benefit to the Science Mission Directorate as well. So all of these different elements within NASA and within the space enterprise are going to benefit from the efforts to work on solar electric propulsion, which you could see on the graphics on the bottom of the screen. That the graphic to the right is a Hall thruster, and then the ones to the left across the bottom are solar array panels that allow you to power up these Hall thrusters. In addition to solar electric propulsion, which gets things very efficiently, 5 to 10 times more efficient than chemical propulsion to and from Mars, we also have to figure out how to get down to the surface of Mars. This we refer to as EDL, or entry, descent, and landing. The technologies that we have to get to the Mars surface today are capable of putting something like the Curiosity spacecraft that Jim Green will be talking about shortly down to the surface, and that's about 1 metric ton or 1,000 kilograms down to the Mars surface. However, to do things much more large, much more significant in mass, such as putting a crewed capsule down to the surface of Mars, requires us to have EDL technologies that we do not have in hand today. And there are several different elements of this. Just like the Curiosity landing, you have to go through an entry phase where you have to use the atmosphere to slow yourself down, and then a propulsive descent stage and a final landing stage. All three elements require technology developments to be able to do human crewed missions to Mars, and the Space Technology Mission Directorate is working on those technologies today so that when we do eventually send our folks to Mars, or if science decides to go to larger payloads to the surface of Mars, we will have those technologies ready to go at that point. The last element that I was going to discuss is that in order to do deep space human missions, and in fact more capable science missions, we also have to work on the communications to and from our spacecraft. Today we use Ka band radio transmission to take information to and from Mars, and we could do about 20 megabytes per second as a maximum capability, and we need to be able to do 10 times or even 100 times that capability. That really is not currently feasible with standard radio transmissions, and so we're working on what's called laser communications or optical communications that will, for the same power level, allow us to do 10 times or even 100 times the bandwidth of communications. And certainly if you're having astronauts there that are capable of gathering significant amounts of science data compared to our robotic missions today, having that higher bandwidth in communications becomes essential. But in partnership with Science Mission Directorate today, even they are looking for substantially greater capability in optical communications. So we're partnered with both mission directorates to advance those technologies. We are also looking at composite structures, and how they are implemented is going to be discussed by Chris Crumley a little later on. With that, I'll hand it back.
Thanks very much, James. Okay, let's go to Jim Green.
Thank you very much. You know, scientifically speaking, NASA's really been on the journey to Mars for a number of years. You know, we have a series of orbiters and 2 rovers that are currently very healthy that's on that surface. And I don't know if you've seen Mars lately, but it is truly a beautiful planet. It has fabulous vistas. It has a number of resources that we're finding out about with our orbiters and our future plans. And we are planning to move towards human exploration of Mars. And these are essential scientific experiments that we have to perform and resources that we have to find. May we have the first graphic, please? So here is what's been happening at Mars. Our operational satellites in orbit, Mars Odyssey, Mars Reconnaissance Orbiter, and MAVEN are all NASA assets. But we also have international partners, such as the European Space Agency's Mars Express, and India has now joined the fray with their MOM mission, their Mars orbiting mission. On the surface, we have Opportunity and Curiosity that are making great progress scientifically and looking for resources and understanding the origin and evolution of the planet from a geological perspective and from an atmospheric perspective. Our current plans for the next several years will be to land a platform called InSight, launched in 2016. InSight is designed to be able to deploy seismic and heat flow measurements that will enable us to understand much more about how active the planet is. And that's important, of course, for human exploration, to know if there are any Mars quakes or any dangers associated with that kind of activity. In addition to that, we have partnership with the European Space Agency. They're leading the Trace Gas Orbiter, which will also be launched in 2016, looking for a variety of trace gases in the atmosphere, such as methane, which might lead us to an understanding of whether there is current life on Mars or not. Then, in 2018, ESA's leading their rover called the ExoMars rover. It's going to be looking for organic, molecular organic material, and NASA is a part of that particular mission. And finally, we're working hard right now on the science rover we call Mars 2020. We haven't named it yet beyond that. But Mars 2020 is just a highly capable rover. It's very similar in architecture to Curiosity in terms of how we will land it, but it has a completely different set of instruments. It has high-resolution cameras. It has make fine-scale mineralogy measurements, and it'll be able to core into the rocks and allow us to understand the detailed geological history of Mars and cache those rocks for potential return to the planet so that we can understand even more about it. In addition, Mars 2020 has some special instruments. It has an instrument from Spain, which is a detailed weather station. It also has a ground-penetrating radar from Norway, and those are important to understand the daily conditions on Mars, but also understand what the resources that might be tapped right underneath the rover, perhaps even finding aquifers if they exist in that location. In addition to that, we have our first major human exploration and space technology instrument that's going to be able to intake the CO2 from the Mars atmosphere and be able to extract oxygen out of it. This is an important resource, of course, for human exploration. We need to perform these tests at Mars to understand how they would operate. And of course, oxygen can be breathed. It would also be an important component for rocket fuel and other resources that it could be used for. So scientifically, we have a fabulous program. The next set of instruments that we put in orbit and that we put down on the ground on Mars are all steps along that journey as we understand and reveal the secrets that that planet will hold and enable humans to explore it further in the future. So with that, let me turn it back over to Trent.
All right, thanks a lot, Jim. So just a reminder, you're going to see the Journey to Mars graphic. Will show up periodically throughout the program. You can find this graphic online, though, on the homepage of nasa.gov. It's the image of the day today. And our friends at the Kennedy Space Center in Florida have a great view of it on the video on the press site, and we'll go there now. So on to you, Mike Curie.
Okay, thank you, Trent. You can see it, the graphic on the wall behind me, and we'll next talk with Mike Bolger about what is going on. Mike?
Yeah, well, very good. Well, hey, it's launch week, right? And that's a wonderful thing. At Kennedy, it's almost like there's a buzz in the air during a launch week. You can feel it. If you've been here for launches in the past, you probably appreciate it. In my mind, it makes Kennedy one of the most special places on Earth. And if you've been to a launch before, you probably feel the same way. If you haven't, hopefully you will by Thursday, because it is really an amazing thing to watch a launch and to be a part of our NASA's programs. So today I wanted to give you a little more of a terrestrial perspective of what we're doing to get ready for the exploration to Mars. And I know many of you have been on the tour buses that we had today, and so you've seen a lot of our assets. But what I wanted to do is tell you some of the work that we've been doing to upgrade our launch infrastructure, our facilities, our ground systems, and our operations processes that we're upgrading to create what we call the 21st century launch complex of the future that we will use as the departure point for our SLS and Orion rocket and spacecraft on our journey to Mars, and also which will support other government and commercial users as we go forward. I'm going to talk a lot about flexibility and adaptability because that's really one of the key tenets of our program down here as we've tried to upgrade our systems. We've eliminated the ground systems and the launch pads that were built specifically for the space shuttle, and we're now replacing them with a more streamlined and flexible architecture that will support SLS and Orion and the evolution of the SLS and the Orion as well as other government and commercial launch vehicles. So at Launch Complex 39B, we've removed the shuttle fixed service structure and we're moving towards a clean pad architecture. So that means you won't have the fixed structure that is specific to a launch vehicle and a spacecraft on the pad that will actually roll out as a part of the mobile launcher. That clean pad approach gives us a more flexible, adaptable way of dealing, again, evolving with SLS and Orion and someday launching other rockets out there as well. We've erected 3 500-foot tall lightning towers out at Pad B. We're implementing a new universal flame deflector and flame trench. We should award that contract this month. And if you drive by there, it's just a beehive of activity with other infrastructure upgrades. We're doing power mods. We're upgrading our environmental control system. We've refurbished our cryospheres. Really just a hub of activity going on out there. Across the street, we've got the iconic vehicle assembly building, 500 feet tall. It's got 4 high bays, each high bay big enough to hold a Statue of Liberty, just to give you a sense of perspective of how big that building is. And inside of there, in high bay 3, We've taken out the old shuttle platforms, the work platforms, and we're in the process of implementing 10 new work platforms. What's neat about the new work platforms is that they can move up and down, so they're adjustable. They can go 10 feet up or 10 feet down, and each has a insert for the platform that conforms to the outer mold line of the launch vehicle or of the spacecraft, and so that, again, allows us to evolve. We can change out those platforms as we move forward. Other projects in the vehicle assembly building, we're taking out the old copper cabling and implementing fiber optics. We're a new FireX system. We're doing door refurbishment on the big doors on the sides of the VAB, and a lot of low voltage power mods, amongst many others. It's a 50-year-old facility, and we're really making sure that it will be pristine as we move forward with the new programs. In the Launch Control Center, which is right next to the vehicle assembly building, we've made a lot of changes to our firing rooms. Firing Room 1 is going to be the firing room that we use to process SLS and Orion. We've equipped it with new state-of-the-art computers, a new command and control system. We're in the process of working on the software. We're using an open architecture that will allow us to evolve and support the engineers who will sit in the firing room to do the processing and ultimately the launch countdown and the launch of the SLS and Orion. In Firing Room 4, we've moved in a different direction. We're transforming that into a multi-user control room. So what we're doing there is we're setting up a room that will allow future customers or future spaceport users, future 21st Century Launch Complex users to come in, establish their own command and control system. We can actually divide it up into 4 individual quadrants so that we could process more than one rocket at a time at a firing room 4. And so again, we're making major changes and setting ourselves up so that we can support many different kinds of rockets. The mobile launcher, hopefully you saw that if you had a chance to be a part of the tour. It's just north of the vehicle assembly building, 400-foot structure. It's really the primary interface to our SLS and our Orion launch vehicle and spacecraft. We're very busy on that right now. You probably saw work going on. We're working on both tower mods and also platform mods, so that you got a platform, you got a tower, and then all the ground systems run through umbilical arms to actually touch the launch vehicle and the spacecraft. That mobile launcher was originally designed for a Ares 1X rocket, so we're doing extensive modifications to strengthen it for the bigger, the larger SLS rocket. We're also preparing it for all of the ground systems that will run through that. So those are the structural mods. At the same time we're doing that, we are designing our new ground systems, so these will be the systems that provide the cryos, the purge air, the power, and the data from the ground to the rocket. We're working on the designs of those. We'll begin the fabrication this year, and we'll start outfitting towards the back half of 2015. We're also working on the umbilical arms, so that's the structure that creates that physical interface between the ground and between the rocket. The umbilical arms are being manufactured now. We're starting the testing over in our launch equipment test facility where we test all of our interface points before we actually use them for a launch countdown. Let's see, inside the VAB, if you had a chance to go in, we've got a crawler transporter number 2. We're doing extensive mods to that. That's it's like about 130-foot by 120-foot tank-looking structure that we use to roll the stack out from the vehicle assembly building to the pad. It's undergoing 20-year life cycle modifications. It's been in use since the Apollo program. Really cool structure. Kind of reminds me of something you'd see in a Star Wars movie or something like that if you get a chance to see it. We've completed most of our refurbishment projects on that. Again, we've done things with control systems, with roller bearings. We've done structural mods to support the new big rocket. We're right on track. Next year, we're going to do mods for what's called the jacking, equalization, and leveling system, which allows us to go up the slope of the launch pad and keep the rocket perfectly vertical. So we're going to be replacing that system in the next year, doing really well. Right on track. So kind of big picture to step back. There's lots of other work going on across the center as well. We're developing our concept of operations and so forth. But big picture, the progress is real and it's tangible. And if you're driving around the Kennedy Space Center, you can see it. It's happening, and it's happening fast. So we're really excited for the EFT-1 launch this week. It's certainly a major step in our deep space exploration plan to put astronauts on Mars. And we're also recognizing that first SLS launch is coming out as fast, too. So Chris Crumley is here with us today. I introduced him. He's from the SLS program to tell you about the great progress that we're making on the SLS.
All right. Thanks, Mike. And I appreciate the opportunity to be a part of this panel on the journey to Mars. We're getting ready to witness the next steps in that journey with the launch of Orion on EFT-1. Now, for the capability that we're building, SLS will be the largest rocket ever built. The thrust of that rocket will be 10% greater than the Saturn V rocket that took our astronauts to the moon. And as we continue to evolve the rocket, it will grow to even 20% greater than that thrust. It will transport astronauts further into space than ever before. The first SLS mission, the EM-1 mission, will be 50% taller and deliver twice the mass of the largest rocket that we have today, the Delta IV rocket that's going to launch on Thursday. Wherever our nation wants to go, SLS can take us there. SLS is a unique, long-term investment designed to be used for decades to come, but it's only part of the ambitious human spaceflight program that we have that includes the International Space Station and commercial crew. The next step is EM-1, and the capability to reach the moon and beyond is being constructed today, as Mike was just talking about what's going on here at the Kennedy Space Center. We're making steady progress in constructing the first elements, and many will go into test campaigns in the coming year. The boosters, based on the shuttle but adding a fifth segment. You see one being fired here in the graphic in the lower quadrant. Each of these boosters is going to provide the thrust, 3.5 million pounds of thrust apiece, to take the total thrust of the SLS to 8.4 million pounds at liftoff. We're planning on a motor firing in early spring of 2015, and many of the components that will be ready for the EM-1 launch are constructed today. The engines, the RS-25, those engines exist today based on the shuttle main engine with a few enhancements, including a new computer called the engine controller. We're making the enhancements for new inlet pressures and new temperatures for the size of the core stage that's feeding the engine. 16 of those engines are in storage right now at Stennis, and testing will begin in the new year of the RS-25 engine. The core stage, over 200 feet long and 27.5 feet in diameter. Qualification and flight hardware is being constructed at the Michoud Assembly Facility in New Orleans, Louisiana right now. In the upper right in the quadrant, you see the world's largest friction stir welder being assembled, ready to build components of that core stage. Test facilities are being readied right now at the Stennis Space Center and also at the Marshall Space Flight Center to put it through its paces, both structurally and also on test firings of the engines and the core stage together. The upper stage and the adapters are being assembled. The Boeing ULA NASA team completed the negotiations recently, and we now have all components for the vehicle under contract, and development is already halfway through. The interim cryogenic propulsion stage is the same stage that you'll be seeing launching the Orion coming up Thursday. A few enhancements to attach it to the SLS. We're also building the launch vehicle stage adapter. We're building the spacecraft adapter, the same spacecraft adapter that is also on the Delta IV that'll launch on Thursday. We have simulators for that and for the core stage and for the MPCV being constructed today for a test to begin in 2015 to show the structural capability of those components. So SLS, from its inception in 2010, has made it through PDR. We have completed our key decision point C milestone in July. We have been put on a path to complete our CDR coming up later in 15. All this accomplished in just a few short years. Things are being done, things are being assembled and being put together. So if I could have the next graphic. SLS is an evolvable design. As our missions increase in the complexity and our destinations further, the SLS will develop and evolve to meet that challenge. We're looking at multiple cargo payloads as a portfolio of our missions. SLS will be a multi-purpose workhorse for exploration of our solar system. SLS is partnering with academia, industry, and other NASA organizations to improve our affordability and our safety and our performance. Composites for the exploration upper stage. Composite cryogenic tanks. Those are the things that, as we save weight on the upper stage, every pound we save is a pound of payload that we can take to our destination. We're looking at additive manufacturing, 3D printing of metals. How can we analyze those, manufacture those, and inspect those to put those in critical aerospace parts such as engines? We're looking at those today. We're looking at enhanced cryogenic handling, storage and transport, replacement of toxic fuels for our attitude control systems, electric power storage and power distribution, and advanced manufacturing with lighter, stronger alloys. We're looking at a new upper stage and new boosters for the future, new fairings. The fairings can grow as large as 33 feet by 102 feet. Very large structures, very large capabilities to make it on our journey to Mars. But these capabilities are being sized to meet the proving ground today and as we step forward into the journey to Mars. When we add the upper stage, we'll increase our payload capability 50%. When we add the advanced boosters, we'll increase our payload capability 85%. 130 metric tons of capability on this vehicle. But it's not only the mass and the size and the volume that we can take in this vehicle, it's the speed. There is a deep space mission that we're studying right now that we can save 5 years on the transport by flying direct with the SLS. SLS is designed to be evolvable to a variety of missions and capabilities. And we've looked at studies for years on how do we best make our capability and our journey onto Mars. Again and again, our studies have repeatedly led to requirements that can only be met, or most effectively be met, by a large capability Earth-to-orbit vehicle like SLS. We've been studying Mars robotically for over 40 years. SLS is going to enable human exploration of Mars. EFT-1 is the next big step. Go big O.
All right, Chris, thank you very much, and thank you to all of our presenters. And we're now ready to take questions. Here at Kennedy Space Center, I would ask for you to please wait for the microphone, state your name, your affiliation, and because we have presenters in Washington and here at Kennedy Space Center, please let us know to whom you are addressing your question. And we'll begin with Marcia Dunn from the Associated Press.
Marcia Dunn, Associated Press, and I'm not quite sure who would take this. Looking ahead to human expeditions on Orion, to asteroids, Mars, how do you envision the habitat issue? Where will you be hooking habitats to Orion to give some living space on those long journeys? Just like a little update on how all the pieces of that puzzle fit together.
Yes.
We'll take that in Washington, Mike.
So this is Jason Crusan. What we're looking at for habitation for the for Mars journeys and into deep space is we're looking at how do we build out the transit habitats that we need to take a crew from here to Mars distances, and how do we actually build the habitats that we'll use once we get there. So we have an activity called the Evolvable Mars Campaign, and it's an ongoing analysis activity on how we break apart the habitation challenges both for in transit and on the surface. And so we've been analyzing different options like pre-deployment of habitats ahead of time using the solar electric propulsion that James highlighted earlier, about placing the habitats in Mars orbit and or all the way to the surface of Mars, and then having a separate transit habitat just for the crew transportation that would actually be delivered via chemical transit in order to minimize the transfer time for the crew. And then utilizing a segment of that habitat actually for the return trip as well. So analyzing these options of like how do you take a habitation system and break it into modular components that are incrementally launched on aboard a series of SLS and Orion flights, assembled in cislunar space in this proving ground as we described it, first to test those activities and to further understanding of the systems that are in there, but with the intent then to take that system and take it as our transit vehicle stack that we use the crews to go all the way to Mars. So sizing of that habitation into a modular package and figuring out that incremental size that we need to get to the total volume and mass for all the logistics and the crew is where we're analyzing at this point. And we should have some results related to some of the habitation work early in the springtime. In parallel, we actually have an active procurement called the Next Step BAA. It's actually out for active bid right now, And part of that, one of the thrust areas within that BAA is related to habitation and this specific question. So we're not just analyzing this internally at NASA, but we're also asking for inputs from industry on approaches to this modular habitation design option, and asking for industry's approach on affordability, manufacturability, and operability in the proving ground period leading to a Mars transit.
Say one more time, it's next BA, that's broad agency announcement.
Yes, it's the next step broad agency announcement, which closes on December 12th.
Okay, thanks, Jason. Irene Klotz?
Irene Klotz with Reuters. I have, I think, probably two questions, and this is for Chris and maybe also for Jason. Could you just discuss a little bit about what will be the difference in the test flights between the EFT-1 and the 2018 first flight with Orion on it? I mean, with on the SLS. If you could maybe just kind of run through what won't be tested on this flight that you hope to pick up on the SLS first flight, and also maybe just summarize why it will take another 4 years to get that rocket ready to fly.
Well, you're lucky that you're going to have the actual program manager come in and brief here before long and talk about more about what EFT-1 is going to prove out. So I'm going to leave that to the owners of the Orion vehicle and how they're proving it out and what they're doing. But I'll tell you that as far as what EFT-1 will accomplish, they're going to push the Orion harder than any spacecraft that we have had that's built to carry humans than we've done since Apollo. 3,600 miles away. So we've been in the low Earth orbit regime that's been 220 miles away, roughly the distance of Orlando to Tallahassee. We're going to push this out to the distance of Orlando to Anchorage, Alaska. We're going to take it up to 80% of the return velocity that Orion will come back in from the moon or from distances in the cislunar space region. So testing that can't be done on Earth, and is to test out the vehicle itself. As far as why it takes longer to build the rocket that we are building now for SLS, rocket building's hard. It takes a lot to develop these rockets, and we're also working in a budget profile that keeps us working towards an affordable solution. So we're building our components at the rate that we can put that into our budget cycle to develop the core stage that's going through extensive testing, to adapt the shuttle main engines into the RS-25s that are going to be firing and testing those and understanding the new conditions that they'll be flying, to enhance the boosters, to bring that into the 5-segment boosters and to bring those online, and to adapt a new upper stage and the adapters to accommodate those, to bring all that together. But when it does come together, it's over 2.5 times the thrust that or the mass that we're delivering on the Delta IV flight on EFT-1, and we're able to carry the Orion vehicle and its systems out to cislunar space.
Also, could you just clarify what the deep space mission is that would shave 5 years off its travel time with SLS? Is that the Europa mission?
We're looking at the Europa Clipper. We're having a technical interchange meeting with that team here in Kennedy this week.
Okay, a question over here.
Thank you very much. Thank you. Scott Powers from the Orlando Sentinel. I think this question is for James Reuter. The technologies you talked about that are still a long ways from being fully developed, the EDL, the propellant and communications. Do you have a sense for what kind of timetables we're talking about to get those to the point where they'll be able to be used in manned missions?
Sure. So each one is on a little bit different schedule, and they're essentially timed based on need. So as I alluded to, all of these technologies, each of these technologies, really services more than one specific need. For example, the high-powered solar electric propulsion, we're developing the technologies today. There are component technologies that go into high-powered solar electric propulsion, such as advanced solar arrays and advanced or higher power Hall thrusters. Both of those technologies are fairly mature today. They haven't been demonstrated in space in a large application, The first component that'll probably be ready would be the solar arrays in that case, and we anticipate that high-powered solar arrays that would enable high-powered solar electric propulsion will actually be on orbit, operational by 2018. So it's really near term. It's at the point where we're building the actual flight hardware today, or starting to build the flight hardware for a demonstration mission. And that similarly, the Hall thrusters that go along with solar electric propulsion are not far behind. They would be ready in the 2018 to 2019 timeframe for a demonstration mission as well. If we move on to optical communications, we're testing optical communications in the 2018 and 2019 timeframe in the Earth it's the cislunar space area, specifically geostationary satellite, to show that we could relay optical comm to and from Earth and show high bandwidth communications that would be applicable to commercial satellite utilization, not just for deep space communications. That technology is going to also be find its way onto a science discovery mission that'll probably fly, what is it, Jim, in the
before 2022.
Yeah, in the 2021, 2022 timeframe. And that's where we will actually test out and demo the deep space capability in deep space optical communications. If you look at the EDL technologies, certainly simply increasing the entry, descent, and landing capability relative to Curiosity or the Mars 2020 mission can happen by the mid-2020 timeframe to get all the way to the point where we have able to put, let's say, 10 metric tons, 10 times what we can do today, to the surface or greater, which is what's really required for a human mission, is probably gonna take till about the beginning of 2030 before we have all those technologies in hand, ready to go at that scale. And that means that they're fully demonstrated and ready for that kind of mission. So each one of these technologies is on a different time slot, but that's because the demand for those technologies in some cases have near-term applications besides being used for a human exploration mission to Mars.
Let's take a question from Ken Kramer, then we'll go to the phone bridge, and then Dan Billow is next up at the rear of the room. Ken?
Hi, Ken Kramer for Universe Today and America Space. I have two questions. Let me ask the first one first. For Jim Green, please, can you give us an update on what Curiosity is doing right now? I believe it recently took a sample and fed it into the SAM and Chemin ovens there. I wonder what we have found there and if anything there could be applicable to humans on Mars.
My pleasure, Ken. Currently, what's happening is Curiosity, as you know, is at the base of Mount Sharp. It's starting to interrogate that area. It has now started a completely new scenario in terms of its exploration. It's charted a path, probably more than 30, 40 meters. It's gone up that path, done a little survey along the way, come back, and now it's indeed interrogating certain locations. And as you point out, it's already ingested some of the material, or is in the process of ingesting some of the material that it is decided is the best of that particular area. Those results are currently going on. The scientists are analyzing those, and although that knowledge has not come out yet, some of that may be discussed at the upcoming meeting in San Francisco of the AGU, the American Geophysical Union, which has a major part of planetary science in addition to Earth science and many of the other fields. We have 2 press conferences planned about Curiosity's results at AGU, so I would encourage you, Ken, to be there, or at least listen in when they're given.
Okay, thank you, Jim. Other question I have might be for you or for someone else, and also a follow-up to what Irene was asking. You talked a little bit about SLS launch in Europa. I wonder if there are some other science missions that we could use the SLS for, and what your thinking is about that. Thank you.
Yeah, I'd like to take that one. Indeed, the concept of going direct to the outer planets, and as was discussed earlier, the Europa mission is one we're looking at right now and considering the feasibility of that. Versus ping-ponging to get gravitational assist in the inner part of the solar system is really a revolution in planetary science. It completely opens up the outer part of our solar system. It enables our scientists to be able to plan a series of missions and get rapid access to places like Uranus or Neptune, and perhaps even beyond. As we study the outer parts of our solar system, we also see habitable regions around these giant planets. The satellites are very diverse, and of course our understanding of those is pretty meager, based primarily on ground-based observations and of course the Voyager flybys on some of the outer planets. So there's a huge scientific interest to be able to get to the outer planets more quickly than an 8 to 10 year event that would occur if we had to do gravitational assists in the inner part of the solar system. So as you go through the planetary decadal, you know that there are several missions that do indeed want to go back to the outer planets, such as going to the moon of Saturn called Enceladus, such as going to Uranus, which is a big ice giant. It's very different, actually, in its makeup than Jupiter and Saturn. And we're seeing a lot of storms that are occurring in these outer planets. So it's an exciting time for planetary science, and the SLS could really open up that field.
Alan Boyle from NBC News is standing by on the phone bridge. Alan?
Hello, can you hear me?
Loud and clear. We hear you. Go ahead, Alan.
Okay. I had a question. I don't know who this would be for, but it has to do with the tempo of missions once Orion and SLS go into the operational phase. For example, EM2, that would be the first manned flight, but I think there's a question mark about whether that would get into the asteroid retrieval mission. And then after that, it sounds as if there's kind of an alternating schedule for years going out, that there would be EM1 and then, EM2, and then perhaps Europa Clipper mission, EM3, and then perhaps a Mars sample return mission, EM4, et cetera, et cetera. Is that the sort of pattern that we're going to be seeing with Orion and SLS, where you have one mission a year, and in alternating years you would have a robotic mission as opposed to a crewed mission? Thank you.
Kruzan, I'll take this question. Yes, you alluded to starting in EM2. We do intend at that point to start on a yearly cadence on SLS and Orion. And the actual specifics of order and such that we'll do are really based on findings and advancement of these capabilities that we're going to achieve. When the actual asteroid redirect mission crewed segment is in large part due to when and which asteroid we bring back. And the timing of that will fall into whatever EM mission that aligns best with when that asteroid will be prepared for us and be ready and achievable in cislunar space. But starting in 2020 on a yearly cadence, looking at that yearly cadence to fly on a routine basis and keep on advancing in this proving arm period, the capabilities of SLS and Orion, combined with the capabilities that were asked about earlier related to habitation, deep space, EVA activities, and all the other capabilities we need in addition to those for trips to Mars. And interspersed with that, when science missions and robotic missions also need SLS, that's an additional capacity that could be utilized by them for the timings of their missions. And actually, to lay those out as a concrete sequence at this point in time is premature, because a lot of this is based on how do these advancements go, the budget realities and decisions on these various missions over a period of time, we do have it fully analyzed of the series of capabilities that we want to advance. And you can think about it as a menu of things that we know we need to do, and we'll sequence those in logical order through a regular cadence of EM missions in the 2020s, starting with the first flight.
We have time for one more question here. Dan?
Yeah, Dan Billow at WESH-TV. I think this would be for Mr. Cruzan. How much are we spending every year to get to Mars? What part of NASA's budget is that? And is that enough to get there within 20 years or so?
Yeah, so I'd point you to our current budget information that's available on nasa.gov for our overall human spaceflight endeavors. Again, we're building capabilities that have a wide variety of application. So things like SLS and Orion are fundamental technologies that we need not only for human spaceflight, but enabling in commercial sector and our science mission directorates. So to separate out exactly what is for the specific purpose of humans to Mars is rather difficult. But rather you could look at the amount of money we're spending on various capabilities and advancing those capabilities to be ready for missions to make that advancement. But the budget specifics are all available on nasa.gov.
Okay, Jason, thank you. And that is all the time we have for questions here at Kennedy. So Trent Parada, we will turn things back to you at NASA headquarters in Washington, D.C. Thank you.
All right, thank you very much, Mike and Chris. We appreciate your help from down there. So I'd be remiss in a Mars briefing not to take the opportunity to at least introduce our brand new Mars Exploration Program Director right here at NASA headquarters in Washington. So let me turn over the microphone here to Mr. Jim Watson, our new Mars Exploration Program Director. Jim?
Thank you, Trent. I'm really excited to be here today to join NASA's journey to Mars and to help be able to participate in shaping that program through the science and technology that we do in the Mars Exploration Program. The previous successes of the program have really placed the bar high, but there's still so much more to do in setting the pathway for future human exploration. I'm eager to get started, and I look forward in the coming months to get out in the community and start interacting with the broader team. Thank you.
All right, thank you so much, Jim. Much appreciated. So stay tuned to NASA TV here. We have an Orion flight test status and overview briefing coming up next. We, of course, invite you to follow our work on Mars now, as well as our human exploration endeavors as we push farther into the solar system toward eventual human missions to Mars. And you can, of course, find the latest always at nasa.gov. Follow the hashtag Journey to Mars as well. I want to thank our speakers here in Washington and those at the Kennedy Space Center for joining us today. Thank you for joining. We'll see you next time, and go Orion.